Students, in this video, we are going to look at typical sketches of polar plots for selected transfer functions. So right here you have two diagrams. You can see the two diagrams. Okay. So these two diagrams will tell you where the polar plot will start and where the polar plot will end. This guideline is for a minimum phase transfer function. That means the transfer function which has only poles. Okay. So if your transfer function is going to have only the denominator polynomial, that is only poles, then these two diagrams will help you to find where your polar plot is going to start and where your polar plot is going to end. If your given system is of type 0, okay, you know what is meant by type. A type is nothing but a number of poles lying at the location 0, and order is nothing but the highest power of the denominator polynomial. So that is your order. Okay. If your given system is of type 0, it will start in this quadrant. If it is of type 1, it will start in this quadrant. If it is of type 2, it will start here in this quadrant. And if it is of type 3, it will start in this quadrant. Okay. So these are the guidelines. And ending point will be in this quadrant between these two lines if it is going to be a first order system. If it is going to be a second order system, it will be here somewhere between these two lines. Okay. And if it is a third order system, it will lie in this quadrant, and if it is a fourth order system, it will lie in this quadrant. So we have taken a system like this. G of s is equal to 1 divided by 1 plus s into t. This is of type 0 and order is 1. Okay. So for type 0 order 1, from this these two diagrams, you can judge that it is going to start in this quadrant and it is going to end in this quadrant. So the same thing will happen here if you look at it. So before we justify this particular diagram, let us compute g of j omega for this g of s. So you will get 1 divided by 1 plus j omega into t, and for this term we have computed magnitude and phase. Okay. So let us get 2 points. Omega is equal to 0 and another point at omega is equal to infinity. When you substitute omega is equal to 0, the magnitude becomes 1. Okay. And omega is equal to 0, the angle becomes 0. And when omega is equal to infinity, when you substitute here infinity, the magnitude becomes 0 and the angle becomes minus 90 degree. Okay. So you've got 2 points now. Okay. One is at omega is equal to 0 and one is at omega is equal to infinity. At omega is equal to 0, the magnitude is at 1, but the angle is 0 degree. That 0 degree line is this line. So the point will lie somewhere here. Okay. At magnitude 1. When omega is equal to infinity, the magnitude is 0. That means it will go to the origin and the angle is minus 90 degree. It will align with this minus 90 degree line. Okay, so this is the point. Okay, so the approximate shape is with 2 points we have drawn the graph, but this is the approximate shape which justifies that it starts in this quadrant and it ends in the same quadrant. For polar plots, you know that the lines are like if this is 0 degree, then in the clockwise direction it is negative minus 90 degree, minus 180 degree and minus 270 degrees. So for a type 0 and order 1 system, it starts in this quadrant and it ends in this same quadrant. Okay. So your approximate shape of the graph will be like this. Okay. So the next example is where you have s into 1 plus st in the denominator. That means it is type 1 and order 2. Similarly, you can calculate the magnitude of g of j omega. You got the magnitude as this will for this term the magnitude will be omega, and for this term the magnitude will be square root of 1 plus omega square into t square. Phase is minus 90 degree minus tan inverse of omega into t. So similarly, we have computed 2 points, omega is equal to 0 and omega is equal to infinity. Okay. So you got 2 points. once the first point's magnitude is infinity and phase is minus 90 degree. The second point, that is at omega is equal to infinity, the magnitude is 0 and phase is minus 180 degree. Okay, and before that, if it is of type 1 and order 2, so it is going to start in this quadrant and order 2 systems will end in this quadrant. Am I right? So from your two graphs, it states that type 1 starts in this quadrant and order 2 will end in this point. So the same thing has happened here. Okay, so infinity minus 90 degree, magnitude is infinity, somewhere at infinity the point has to be, okay, magnitude, and the phase angle is minus 90 degree, so it should be at minus 90. Okay, a line parallel to minus 90 degree, and at omega is equal to infinity, the magnitude is 0 and angle is minus 180 degree. Okay, so you got minus 180 degree. So your graph will look like this. The shape of the graph will be like this, approximate graph. Okay. So here is another system where the type is 0 and order is 2. So type 0 will start in this quadrant and order 2 will end in this point, in this quadrant. So your approximate shape of the graph will be like this. The same definition, okay, the same thing what we have done for the previous transfer function, the same thing we have to do here. G of j omega, get the magnitude, get the phase, 2 points, that is omega is equal to 0 and on omega is equal to infinity you get the magnitude phase. Okay, when you substitute infinity here, what will happen? This will be minus 90 degree, again minus 90 degree, so together it will be minus 180 degree. Okay, so and when the magnitude is when the omega is infinity, the magnitude is 0, got the 0. So I think these 2 points satisfies, am I right? This point and this point satisfies these two expressions. So your graph shape will be like this. Okay, so this is another system where the type is 0 and order is 3. Okay, type is 0 and order is 3. So obviously it has to start in this quadrant and order is 3, so it has to end here somewhere between minus 180 degree and minus 270 degree. Okay, so this is the ending point. So similarly we have computed the magnitude and phase, and at omega is equal to 0 and at omega is equal to infinity we have computed the magnitude and phase for g of j omega. So these 2 points satisfies our answer and your graph shape will be like this. Okay, so here again there is another system where the system's transfer function is having a type 1 and order 3. So type 1 should start in this quadrant and order 3 will end in this quadrant. So as usual you calculate the g of j omega and get the magnitude phase for 2 points, omega is equal to 0 and infinity. At omega is equal to 0, the magnitude is infinity and minus 90 degree. Okay, so it's a line parallel to minus 90 degree. You should take a point, and for omega is equal to infinity, the magnitude is 0. So here at this point, the magnitude is 0, angle is minus 270. Starting and ending points. Okay, so your graph is like this. The arrow mark is also important. At omega is equal to 0, it starts. At omega is equal to infinity, it ends. So this is another transfer function with order 4 and type 2. Okay, so when it is of type 2, it should start in this quadrant and end in this quadrant. Okay, and this is another example of type 2 and order 5. For order 5 we have not covered in the initial graph, but let us see what happens to the angle and let us come to a conclusion it ends in which quadrant. Okay, after computing the magnitude and phase, you got such an expression. At omega is equal to 0, you got this answer, magnitude infinity and phase minus 180 degree. At omega is equal to infinity, you got magnitude 0 and phase minus 450 degree. Okay, so minus 450 or minus 90 degree. Okay, so type 2, it starts in this quadrant. Okay, omega is equal to 0, magnitude infinity, phase minus 180 degree. That is satisfied by this point. And omega is equal to infinity, you can see that the angle is minus 90 degree. Okay, and the magnitude is 0. So it comes to the order 5 system, it comes to the order 1 final point, am I right? So for order 5, the ending point will be in this quadrant. Okay, so here is another example where you have only one term 1 by s. So for magnitude of this 1 by s is 1 by omega and phase is minus 90 degree. Okay, so here when omega is equal to 0, omega is equal to 0, magnitude is infinity and angle is minus 90 degree. And when omega is equal to infinity, the magnitude is 0 and the angle is again minus 90 degree because angle is not a function on omega. So from this you can see that it is both minus 90 and minus 90. And only the thing is the magnitude is changing from infinity to 0. That means that the magnitude will change from infinity and it will go till 0. But it will lie on minus 90 degree line. Am I right? Because it is both minus 90, 90. So omega is equal to 0, magnitude is infinity, omega is equal to infinity, magnitude is 0. So you got a line like this. Okay. So we have also discussed some terms which has numerator also, that is this particular transfer function is having a numerator also. Okay, 1 plus st divided by s into t. So let us not go by the guidelines given in the initial slide, that is type and order. We have some guidelines, isn't it? Since this term has numerator polynomial also, we will as usual go by g of j omega for and we'll compute what is the magnitude phase, and for omega is equal to 0 and infinity, let us see what are the points and then try to plot the graph. Okay, so it is 1 plus j omega t by j omega t. You can rewrite it like this. Okay, you have got two terms now here. One has a magnitude of omega t and phase of 90 degree in the denominator, that is 1 by omega t and minus 90 degree plus 1. This is one extra term that you have, plus 1. Okay, so when you substitute omega is equal to 0, for this term the magnitude is infinity and angle is minus 90 degree, plus 1 is there. When omega is equal to infinity, you have magnitude 0 and minus 90 degree plus 1. You can see that this is similar to this case, but only thing is it is plus 1 is in addition. Okay, plus 1 is in addition. Of course, when you plus 1, it means that the magnitude, okay, infinity plus 1, of course, it's going to be infinity. And 0 plus 1, the magnitude is going to be 1. Okay, so the graph that you see here will shift by 1 unit. Okay, so the graph that that was here will shift by 1 unit because both are same, only thing is plus 1 is there. Okay, so at omega is equal to 0, the magnitude is infinity, angle is minus 90 degrees, so a point which is parallel to minus 90 degrees is enough so that you will get a point here. And for omega is equal to infinity, the magnitude is 1. Okay, and the angle is again minus 90 degree. So this will be the shape of the graph. Okay, a line parallel to minus 90 degree and at magnitude 1. Okay, so that will be the shape of this transfer function. So here the transfer function is only s. So it will be G of J omega will be J omega, magnitude is omega, and angle is 90 degree. So at omega is equal to 0, magnitude is 0 and angle is 90 degree. And at omega is equal to infinity, magnitude is infinity and angle is 90 degree. So both cases the angle is 90 degree. But the magnitude varies from 0 to infinity. So your graph will be like this. Magnitude 0 to infinity. When omega is varying from 0 to infinity. Since minus 270 degree is equivalent to plus 90 degree, the graph lies in on this line. Okay. So there is another term 1 plus st, which has a, a magnitude. For this particular term you have magnitude of omega t and 90 degree plus 1 is extra. So what's the difference between these two terms? Plus 1. So that means that we have already seen it will shift by 1 unit. Okay. So you've got magnitude like this and magnitude and phase like this for omega is equal to 0, and for omega is equal to infinity you got magnitude and phase like this. So similar to this expression, but only thing is plus 1. So you have to shift it by 1 unit. So your graph will be like this. So all these explanations will give you an idea on how the shape of the polar plot will be for a given transfer function. So you'll be able to judge what kind of shape the polar plot is going to take. So that was the objective of this video.